Hi, everyone. So, the lessons that we've had lately started out talking about solving systems of linear equations. And then we saw that we could use matrices to help solve them. And then we had a couple of lessons where we've just been talking about matrices and doing some other things with those. But remember, this whole discussion started with us trying to solve systems of linear equations. So, what this lesson is going to be about is what if you have a system of equations, but they're not linear? And we'll see what we have to do about that. So let's go ahead and get started. Now, by the way, I'll just remind you that linear equations represent things like straight lines, and we started a few lessons ago talking about where do two lines intersect. And they were straight lines. Where do two straight lines intersect? And we found the point of intersection. And then when we started looking at systems with three variables, we said that they could be thought of as representing planes in three-dimensional space. So where do some planes intersect each other? But if we start talking about nonlinear equations, then we're not just talking about straight lines or planes. We're basically talking about things that are curved. And when you have a bunch of curves and you want to figure out where they intersect each other, it's a little bit trickier. So I'll give you an example. As a question, how do we solve the following? It's just going to be a system of two equations and two variables. 3x squared plus 2y equals 26. 5x squared plus 7y equals 3. Now, it's still a system of equations, but what makes this different is that the x's are squared, and that's what makes this nonlinear. These are not straight lines, and you can't write these as y equals mx plus b. They're just not straight lines. So we're going to discuss three methods, I think. We'll discuss three methods. And I think I'll show you three methods all for this one problem. And then we'll do a couple of other problems maybe at the end. So method one. Oh, by the way, none of these are going to involve matrices. Matrices were basically a thing we used for linear equations, but we can't really use them here. So method one is going to be substitution. The reason that there are three methods is just because you have different options for the algebra. I think one idea for algebra is substitution. Take one of the variables and solve in terms of the other. So from the second equation, we could use the first or the second. I just chose the second one. I think we could probably try to solve for y in terms of x. Like I could get y equals 3 minus 5x squared. So y is 3 minus 5x squared over 7. All right, and then the idea is we'll substitute this. Into the first equation. So this is really similar to what we did with some linear systems. Solve for one variable in terms of the other, and then substitute into the other equation, the one that you haven't used yet. So we haven't used equation 1 yet. So the first equation would look like 3x squared plus 2. Instead of 2y, we're going to write 2 times this. And it equals 26. So we did the substitution. We substituted this in for y. Now what we have is one equation with one variable, and we can try to solve one equation, one variable, and that means that we can probably solve for x. So let's start by doing something about these parentheses. I've got a 2 over 7. That doesn't really simplify nicely, but do 2 times 3 over 7 is going to be 6 over 7. minus 2 times 5 over 7 is 10 over 7x squared. And the right-hand side is still 26. You know, and you've done this kind of thing in algebra classes before where you're just given one equation with one variable. You got to solve for x. I think what we can do here is, let's see, 3x squared minus 10 over 7x squared. So combine those, because that's some number of x squareds minus some other number of x squareds. I guess the 3 could be thought of as 21 over 7. 21 over 7 minus 10 over 7 is 11 over 7, right? And then what about this 6 over 7? Let's just bring that over to the other side, like that. So I'm trying to solve for x, and we made it a little bit simpler. The way that I'm going to do this algebra, I guess we could divide both sides by 11 over 7, or multiply both sides by the reciprocal. Let's see, is that what we want to do? What I decided to do is I decided to multiply both sides by 7. I multiplied both sides by 7, multiplied this by 7, and then I subtracted, I guess I multiplied this by 7 and got 6. So I wound up with 176. Divide both sides by 11, and 176 divided by 11 winds up being 16. So look at this. We're getting, I guess, x equals 4 and x equals negative 4, right? Those are the two things that could possibly get you 16 when you square them. So it looks like we're getting more than one answer. Are we done with this? Well, now we need to find y. You know, remember what we're doing here. We had two equations and two variables. I'm expecting answers to be x comma y. So remember that we said that y was 3 minus 5x squared over 7. So y is 3 minus 5x squared over 7. And at x equals 4 and x equals negative 4, we need to solve both of them. So I guess when x is negative 4, you can solve this. I'm going to just kind of skip to the answer just to save a little bit of arithmetic time. But evaluate this, and you should get negative 11. And when x is positive 4, 3 minus 5, positive 4 goes in. You also get negative 11. So what can we say? We're going to say we found two solutions, didn't we? Because we found two different x values that work. For each x value that we found the y value. So the solutions to this system, there are two of them. It's negative 4 comma negative 11 and positive 4 comma negative 11. Okay, so we did it, and we did it using substitution. By the way, I'll just remind you that when we talked about linear equations, for linear systems, we said this can never happen. Like, a linear system will never have just two solutions. A linear system has, you know, there can be one solution, there can be no solutions, or there can be infinitely many. But for nonlinear equations, that rule goes out the window, and it is possible to have something like two solutions. So that was method 1, substitution. Not too bad, right? Solve for one variable in terms of the other, substitute it into the other equation, continue from there. I'll show you another method. Method 2 is elimination. And elimination is something we talked about for linear systems, but now we'll talk about it for this problem. I'll write the problem again. It's the same one that I want to talk about. I just want to show you a few methods, and then you can see how they compare. So the goal of elimination is to eliminate one of the variables. Now, remember when we did this for linear systems and we did things like adding two equations together, maybe multiplying an equation by a constant first and then adding equations together? That's basically what we're doing. Well, out of these two variables, which one would be better? Which one do you think would be more convenient for us to get rid of? I think the x squared would be nice to get rid of. Let's say we want to eliminate x because, you know, the y's are just y, but the x's are x squared. So if we could somehow knock out the x's, that would help us. Now, the x squared up here has a 3 in front of it, and the x squared down here has a 5 in front of it. So if I add these two equations together, it's not going to help. You know, we'll get 8x squared. So I think we need to do that step where we multiply the equations by constants. So what I decided to do was 5 times the first equation. And also, I did -3 times the second equation. So the first equation becomes 15x squared plus 10y equals 130. The second equation becomes -15x squared minus 21y equals -9. And now you can see why I chose 5 and -3. I chose them because I saw that that would get me a 15 and a -15. 3 and 5, I thought 15 is going to be the way to go. What's it going to take for me to get a 15 and a -15? And I did it this way. I guess another option is instead of 5 and -3, you probably could have done -3 and +5, or sorry, -5 and +3. I'm just saying one of these had to be positive and one of them had to be negative. So now we add them, right? Add these equations together. And what do we get? We have the 15x squareds cancel out. 10y plus -21y is -11y. 130 minus 9 is 121. -11y equals 121. So y is -11. So we still need to find x. This time we found y first. So now substitute y equals -11 into one of the original equations. And it's your choice which one you want to work with, the first equation or the second one. 3x squared plus 2y, you know, either one. I'll use the first one, I guess. 3x squared plus 2y is 26. And that's going to be 3x squared minus 22 equals 26. The 22 and the 26 will be combined with each other. Be careful, though. Remember, you're adding 22 to both sides. To get rid of the 22 on the left side, you want to add 22 to this, add 22 to this. So we get 48. I know sometimes you see like a 22 and a 26, and you think, oh, they're only 4 apart, right? You put a 4. But no, you have to add 22, add 22. So 48. And then you get x squared is 16. And we get x equals -4 and x equals +4. So for the y value, -11, we found the x values, -4 and +4, which means two solutions. It means negative 4 comma negative 11, and positive 4 comma negative 11. Of course, these are the solutions that we found earlier. It's because this is the same problem. We just solved it using a different method. So, out of the two methods, substitution or elimination, which method do you prefer? Which one do you think is better? Well, personally, I think they take about the same amount of work. And yeah, I think I'm going to leave it up to you as to which of those two methods you wind up using. Just like with linear systems, I might use one method or the other depending on the problem. If it looks really convenient to do elimination, then I might do that. But if it looks convenient to do substitution, then I'll do that. Now, I said that there were actually three methods we were going to discuss. So method 3 is a graphical method. Yeah, we haven't drawn any pictures today. We're talking about the intersection of two curves. So notice we're still talking about the same system, okay? So notice that both equations describe parabolas, right? What do we have? We had the system 3x squared plus 2y equals 26, and 5x squared plus 7y equals 3. Are these parabolas? I mean, they don't look like they're in the usual form. But yeah, we could take this and rearrange each one. Just move some pieces around. I guess if we tried to solve for y, you would get 2y equals 26 minus 3x squared. And then you could go one step further, divide everything by 2, and you'll get y equals negative 3 halves x squared plus 13. Over here on this one, you'd get 7y equals 3 minus 5x squared, which can be turned into y equals negative 5/7 x squared plus 3/7. I'm going to circle these. This is not the form that they were given in, but this is equivalent to the original system. These are two parabolas. I can tell because it's x squared, right? It's just y equals something times x squared plus a constant. These are quadratic functions. So they're two parabolas. Also, I noticed that they both opening downward. Remember, parabola can open upward or downward. I know that these open downward because there's a negative coefficient in front of them, negative 3 halves or negative 5/7. So yeah, these both open downward. And what we can do for this graphical method is graph them and look for points of intersection. Now, we've already solved this problem with algebra, but I want to show you what this looks like visually, so I'm going to graph these. It's a little tricky to graph parabolas that have fractions in them, but you've learned about that in algebra classes. You know about finding like the vertex of a parabola. You could try to graph it from there. I mean, I can see what the y-intercepts are. Maybe that helps. I could find the roots, and that would help. So we would know the y-intercept of each one, and we could find the x-intercepts of each one. We know they're parabolas that open downward. Actually, yeah, this is not that bad. So I drew a picture of these and found that it looks like The first one has a y-intercept of 13, so when we draw this, we have to make sure that we set up the scale so that we go at least that high. So what I'm going to do is I'm going to say this goes 5, 10, 15 to make sure that we can get that 13 in there. And, the horizontal scale doesn't have to be the same scale. We could set that up a little differently. So I set up the horizontal scale. I think what I did was I probably found the roots and just decided to go kind of 1, 2, 3, 4, 5. That scale is going to work for us. All right. Oh, down here, I'll go ahead and mark -5, -10, -15. All right, the one with the y-intercept of 13, it's up here, it opens downward, and it goes something like this. This is, well, you know what? I was about to write the y equals, but let's write it in the original form. Let's write it in the original form that the problem had. You know, there were two equations, and this was, let me remove that other page. This was the 3x squared one. So this was 3x squared plus 2y equals 26. Looks like that if you graph it. The other one had a y-intercept of only 3/7. So 3/7 is pretty close to down here at the origin. And it looks something like this. All right, that's pretty close. And this is the one that's 5x squared plus 7y equals 3. So yeah, this is the intersection of two curves. And now maybe you can see why they intersect at two different places. And if we drew this perfectly to scale, which I probably didn't draw it perfectly, if we did, we would find that there's this point of intersection here and a point of intersection here, and that those are the points -4, -11, and +4, -11. So I think that if I were given a system and I'm trying to solve it, I would probably use method 1 or method 2, but I did want to at least do this for this one so that you could see, yeah, we're talking about the intersection of two curves, and this is why they intersect in two places. And it actually makes sense that the two places they intersect are kind of symmetrical, -4, -11, and +4, -11, because they both have kind of a axis of symmetry at the y-axis. All right, so we talked about 3 different methods. I think methods 1 and 2 are the main methods. So I'm going to give you a problem, and I'm going to say for this, find all solutions. And you can use whichever method you want out of those 3 methods. The problem is going to be x squared minus y equals 2. And 2x minus y equals -1. So I'd like you to pause the video and give this a try. So, between the substitution method, elimination, or graphing, I decided to use the substitution method. I looked at this and I thought I could probably solve for y pretty easily, like solve for y in terms of x. So from equation 1, I said, well, y is x squared minus 2. And then I could substitute that into equation 2. So equation 2 becomes 2x minus this equals negative 1. One equation with one variable. Can I use this to solve for x? Let's see. I guess I have negative x squared plus 2x plus 3 equals 0. It's a quadratic and it's equal to 0, and I could probably try to factor it and see if I get some x values out of this. So before trying to factor it, I decided to multiply it by negative 1. That's optional, but I did that because I find it easier to factor things when the first term is just x squared instead of negative x squared. And I knew I was going to be trying to factor, so I was like, well, that's going to make it a little easier. So this factors to x minus 3, x plus 1, and I get x equals 3 and x equals negative 1. So those are my x values of my solutions, but now I need to find the y values. So we need to put those in, right? This is substitution, so we're gonna, we substituted this in place of y. We got x's, but now we need to find y. And we need to find it at both of these. So we could say when x equals 3, the best thing to use to try to find y is probably what we wrote above. We said that y is x squared minus 2. So let's just use that. Y is x squared minus 2. So y is 3 squared minus 2. We get 7. The other one, when x equals negative 1, y is negative 1 squared minus 2 is negative 1. I'm leaving a little bit of room here because I want to draw a picture after this. So the solutions, we found 2 of them. When x is 3, y is 7. When x is negative 1, y is negative 1. So we found the solutions 3, 7, and negative 1, negative 1. If you use the elimination method, you should also find the same 2 solutions. So I have a couple of things I want to say about this. We answered the problem. One thing I want to say is you could check these solutions. Remember, you could say this is x, this is y. Put it into the original problem and make sure both equations are true. Put in x equals 3, y equals 7. Does equation 1 wind up equaling 2? Does equation 2 wind up equaling negative 1? And then that would confirm that this is a good solution. And then do it with the other solution also. So, if you have time, you can check your answer. The other thing I wanted to say is I also solved this using the graphical method. So maybe I'll show you a quick sketch. Because I looked at this and I said, well, the first one is going to be a parabola. And the second equation is going to be a straight line. So let's see. All right, I guess for graphical, I would say x squared minus y equals 2, 2x minus y equals -1 can be thought of as y equals x squared minus 2 and y equals 2x plus 1. You see that that's just a rearranged version of the original equations? But the nice thing about rearranging them into the y equals form is that I can tell that this first one is a parabola shifted down 2 units. So let's draw the first one. Okay, so that's y equals x squared minus 2. It's the standard parabola, but it's been shifted down 2 units. And then y equals 2x plus 1 is going to be a straight line with a slope of 2 and a y-intercept of 1. So I'll draw the y-intercept at 1. And then I know a slope of 2 means for every 1 unit I go to the right, I go 2 units up. So this is the intersection of a parabola and a straight line. And where do they intersect? Well, this point down here looks like it's at -1, comma, -1. And this point up here, if you're careful with the graphing, then you would find that this is the point 3, comma, 7. So that's why it makes sense that we had two solutions, 3, comma, 7 and -1, comma, -1. Okay, so I think I'm going to move this page and let's do a couple more problems. I'll do the next one for us. All right, so this one is going to say to solve the nonlinear system x minus y equals 4, xy equals 12. So I'll show you what I have in mind for this one. By the way, you've probably noticed I'm calling these sorts of things nonlinear systems, even though sometimes one of the equations is linear. You know, like in the previous example, one of the equations was a straight line and one of them was a curved line. So even though one of them was linear and one of them was not, we could still just call it a nonlinear system. So I think that this first equation is a straight line because we could solve for y and it would, you know, it would be a straight line. But this is the first time we've seen x times y appearing in one of these problems. So let's see what we can do about this. All right, so actually, I think because of the xy equals 12, I think it would be difficult to do elimination method on this. I think substitution method is going to be better. You know, because elimination method, we try to get rid of the x or the y, usually by adding equations. But because that has that xy, I don't think that's going to happen. So let's do substitution. And I think from equation 1, we could either solve for y in terms of x or x in terms of y. I actually did solve for x in terms of y. I said x is 4 plus y. And then we're going to substitute that into equation 2. So instead of xy equals 12, it's going to be this equals 12. All right, let's distribute, and we get 4y plus y squared equals 12. Can we figure out what y is from this? Well, let's rearrange it. Let's write y squared plus 4y minus 12 equals 0. Because you know that when we have a quadratic that we're trying to solve, a quadratic equation that we're trying to solve, we like to make the right-hand side 0. So I brought the 12 over to make that happen, because then we can factor it and have something that's factored and the right-hand side is 0, and we'll be able to figure out what y is, you know, once we get this. So does this factor nicely? If it factors with, you know, whole numbers, then that's great. If it doesn't factor nicely, we could try to resort to the quadratic formula if we have to. But yeah, this does factor to plus 6 minus 2. Y plus 6, y minus 2. So this means that y is negative 6 or y is 2. So in this problem, I found y first, and now we need to find x. Usually at this point in the problem, you already have something on your page that you could use to help you get x. I think we'll use this, right? We said x equals 4 plus y. So let's check when y equals negative 6. We'll figure out what x is. So x is going to be 4 minus 6, which is negative 2. And let's check when y is 2. X equals 4 plus 2, which is 6. So we can write our answers. We found two solutions. We'll write them as x comma y. So even though we found y first, make sure you rearrange them to be x comma y and x comma y. And that looks good. By the way, you know, I mentioned earlier that you can check your answers. Let's do that for this one. I haven't done that for any of them today, so let's just do it for this one. It's optional. If you did all these steps carefully, then you should get the correct answers. Oh, by the way, just as a quick little side note, a lot of these problems seem like they have two solutions. There's no guarantee that there are going to be two solutions. You might get a problem that has one solution or 0 solutions or 3 solutions. You know, it could be any number. With nonlinear systems, you never know. It's just a coincidence that a lot of these seem like they've had two solutions. Okay, so let's check the answers. So really quick, this one, you know, if this is supposed to be my x and this is supposed to be my y, going back to the original system, right? In the original problem. Don't check them in the middle of the problem. Make sure you go back all the way to the beginning. So first equation would say x minus y. So negative 2 minus negative 6 does equal 4. Yes, that checks out. I'll just put a little check mark there. Second equation. xy does equal 12. Yes, negative times a negative equals a positive. Good. So that means that this solution looks good. But we should also check the other one if we want to be thorough. So let's check this x and this y. In the first equation, x minus y, so 6 minus 2 equals 4. Yes, that works. And in the second equation, 6 times 2 does equal 12. Yes, this works. So you see, checking their answers was pretty fast. Let me section this off. That's pretty fast, right? So do that if you want to be extra sure. All right, I've got another problem for us. This one I'm going to ask you to try. So let's see. I'm just going to say solve. You can use the method of your choice as long as you show work. I think you should use the elimination method or the substitution method. Um, yeah, because, graphing, we talked about the graphical method a little bit, but it's really not as precise if you're trying to do it by hand. Well, I guess you could, but these would be hard to graph by hand and get it just right. All right, so this is going to be your problem. X squared minus y squared equals 1. 2x squared minus y squared equals x plus 3. So I'd like you to pause the video for a couple of minutes and see what you get. So, faced with the decision of using the elimination method or substitution method, I think I decided to try the elimination method on this one because I saw like a y squared and a y squared. It doesn't really look like I should add the equations right now, but they almost line up, right? It would be better if we had a y squared, like if one of them was positive and one of them was negative. So I decided elimination method because they almost line up, but I decided to, let's see, I decided to add -1 times equation 1 to equation 2. I mean, we can do those kinds of steps even with nonlinear systems. So equation 1 did not change. Equation 2, the left-hand side, let's see, 2x squared got minus x squared added to it to give me just x squared. And the minus y squared got a plus y squared added to it to just give me a 0 here. So then I have my equal sign. And on the right-hand side, the x plus 3 got a, what did it get added to it? -1 gets added to it. So instead of x plus 3, it's x plus 2. So we eliminated y from equation 2. We could probably try to use equation 2 to just find x, right? Because equation 2 is now an equation that just has one variable. So let's try that. Equation 2 says x squared equals x plus 2. Let's do a little rearranging and write it as x squared minus x minus 2 equals 0. And we could solve for x. Seems like in this section, most of these, once you get to this point, most of them factor. This does factor. X minus 2, x plus 1. So I found x equals 2 and x equals -1. So two values of x, and now we need to find y. Now find y. We should find it for each one of these, but just a quick note, I'm going to have to put these into one of the equations. I guess you could go all the way back to the beginning and say you could use equation 1 or equation 2, and you're going to put in x equals 2 and x equals -1. So I decided to go back to equation 1. From equation 1, it says x squared minus y squared equals 1, and I rearranged this to y squared equals x squared minus 1, which got me y equals plus or minus the square root of x squared minus 1. Don't forget the plus or minus. Now I said, all right, what happens when x is 2? When x is 2, I get plus or minus the square root of 4 minus 1. So I get plus or minus the square root of 3. That's that's two different y values. So when x is 2, we get y equals square root of 3 or minus square root of 3. And then we should also check when x equals negative 1, what does y equal then? Plus or minus the square root of negative 1 squared minus 1. That's plus or minus 0. That's just 0. So the solutions that we found. How many solutions did we find? Well, we found two different x values. But for x equals 2, we have two different y values. And for x equals negative 1, there's only one y value. So, okay, altogether, we found the solution 2 comma negative square root of 3, 2 comma positive square root of 3, and negative 1 comma 0. So we actually found 3 solutions to this. So yeah, a few minutes ago, I was talking about how it seemed like coincidentally a lot of the problems in this section seemed like they had 2 solutions, but that doesn't always happen. Well, here's an example. We had 3 solutions instead of 2. And remember, you could check these, put these into the original equations, make sure the equations work. I mean, the equations have y squared, so I guess you'd be putting in the square root of 3 and squaring it, so it's not so bad. Putting in negative 1 comma 0, that one would probably be the easiest one to check. All right, so I'll leave this here just for a moment in case anyone is still copying it, but that was the last example for the section. All right, so that was our section on systems of nonlinear equations. Those last couple of examples we did were just some extra ones that I'm glad that we had time to fit those in. But yeah, so main idea is we use the same kinds of algebra tricks that we are used to, right? So you can use substitution method or elimination method, but we don't really use matrices to solve these. The types of nonlinear equations that I'm interested in are mostly the types that we saw today. You know, they were polynomials. You might have things that are squared. You might have x times y, things like that. I'll tell you that we only have this one lesson on nonlinear systems, but you could imagine that this is a topic that you could do more with it, right? Like there could be systems like this that involve trig, or systems like this that have exponentials or logarithms, and it's something that you could devote a lot of time to. But in this course, we just have this one lesson on it, just to give us a little introduction to it. All right, so that's going to be it for today. So thanks for watching, and take care.